Let us go to the next property that is called as the conformational mobility or the ring inversion. So for this, I will take a simple example of the cyclohexane. Okay. Now I will show you two more structures and you will tell me what is the difference between this. This is the second structure. Okay. And this is the third structure. Again, I'm repeating. This is my first structure, simple cyclohexane ring. Okay. This is my second structure. Something has happened if I'll compare it with the first one. And this is my third structure. Again, some changes compared to the first structure. So what is the relationship of the first structure with the second and the first structure with the third? What is this? What these concepts are called as? Okay. Now there are two words I'm going to introduce. One is the ring inversion. Vijeta, you're absolutely right. That is first to second. I will call it as a ring inversion. Now, what is the ring inversion? I can see here there is some intramolecular arrangement changes. It has happened. Now, if I'll see at this particular this first carbon here, there is axial bond and there is an equatorial bond. Okay. Now, in the case of this axial and equatorial bond, suppose if I'm drawing this axial and equatorial bond in the case of this first carbon, let's say at this first carbon, this is my axial bond and this is my equatorial bond. Over here also, this is my axial bond and this is my equatorial bond. There are two bonds over here. Now in this case, in the first structure, what I can see is my axial bond is on the top or above the plane. And this is my axial bond is below the plane, pointing towards below the plane. So in the case of the first structure and the second structure, this first structure and the second structure, what is happening? There is some changes in the structure, but if I'll keep this structure on the top of this, they will not match with each other. They're not superimposable or they're not exactly equivalent structure. So when you have some kind of the conformational changes within the molecule and these changes are not equivalent to the previous one, then we call this concept as ring inversion. But look at the second structure now, third structure now. There is again changes, there are changes in the molecule, intramolecular changes. But look at the structure. If I'll keep this ring on the top of the previous, this is equivalent. I'm not saying it is original. Definitely it's not original because you can see all the carbon have changed their position. Now the second carbon is here. Previously the first carbon was there. So I will call it as equivalent. It is not original. So some conformational changes are there. Intramolecular moments of the attached bonds are there, but they are equivalent to the previous one. This concept, we call it as pseudo rotation. Pseudo rotation. Now this to this, if you'll see, ring flipping, actually the pseudo rotation involves two ring flipping. What will happen? First, the ring will change from this structure to this structure. When this ring will flip, we will get the previous structure back, equivalent structure back. So in short, the pseudo rotation involves two ring flipping. So when you have the intramolecular movement of the atoms or the intramolecular changes in the conformation, which brings about a new structure which is not equivalent to the previous, we'll call this concept as ring inversion. And if I will change this to the another structure which is equivalent to the previous one, I will call this concept as pseudo rotation. Okay, so these two words are different, ring inversion and pseudo rotation. They are not same. Okay, now suppose if I have to avoid this pseudo rotation, what I have to do? I have to create more steric crowding somewhere here. So if I create a steric crowding here, definitely they will not change from one structure to the another structure. Okay, but is it possible for the cyclohexane? Can you give me one example where I can avoid this kind of ring flipping in the case of cyclohexane? You have studied in TY. As we know that tertiary butyl groups are stable in the equatorial position. So suppose if I have this tertiary butyl group here, this will have the equatorial that location rather than the axial location. Now this particular ring will not flip here, because what will happen if the ring will flip? Suppose this is my one structure and this is flipping structure. At the fourth carbon atom, this tertiary butyl group, which was equatorial, it will change its location to the axial. And we know that tertiary butyl group is not stable in the axial position because it will have a 1,3 diaxial interaction. Because of that, this tertiary butyl group cannot be accommodated in the axial position. So it will prefer to remain in the equatorial position. So what is the general concept we have studied in the case of previous, the cyclohexane in the TY? That the rings, cyclic rings, always have a conformational mobility. Conformational mobility. This conformational mobility can be of two types. Either they can have a ring flipping or a ring inversion, in which there is a conformational change, but which is not equivalent to the previous one. Or second type, they can have a conformational change which is equivalent to the previous one. We call it as pseudorotation. This kind of conformational mobility can be avoided if we'll attach the bulkier groups like tertiary butyl group. This tertiary butyl group will prefer to have the equatorial conformation. Now, if you have this kind of structure, it will remain rigid. It will not change its conformation, because as it will undergo any kind of changes in the conformation, this tertiary butyl group will change from equatorial to axial. And when it will change to equatorial to axial, the axial will have the 1,3 diaxial interaction with the any substituent present at the second and the sixth carbon, axial substituent, and because of that it is not stable. So this compound will remain stable in this conformation only. So now we are talking about the medium size ring. So what is the concept here is, in case of smaller ring, suppose instead of this tertiary butyl group, suppose if I'll attach the methyl group, can we have the conformational mobility here? Instead of tertiary butyl group, if I take methyl group, we cannot avoid the methyl. With the help of methyl group, we cannot avoid the conformational mobility. If I attach methyl group here, definitely the cyclohexane will undergo the conformational mobility. Why we cannot avoid? Because everyone knows the cyclohexane which I have drawn here, it's a chair conformation. It's more stable in its conformation. And if you remember, in the chair conformation, if I observe the arrangement of atom across any bond, it is always in the staggered form rather than eclipsed. And since they are present in the staggered form, these methyl groups, they are actually away from the adjacent substituents. And that is, steric crowding is comparatively less. So if I have to avoid the conformational mobility in case of cyclohexane, I have to go for bulkier groups like tertiary butyl. If I attach the smaller substituent than the tertiary butyl group, it is very difficult to stop the conformational mobility. But that is not the case in case of the medium size ring. So what happens in the case of medium size ring? So what happens in the case of medium size ring? I'll just wait a sec. So this is your cyclooctane and this is your cyclodecane. Now if you remember while discussing the structure, what I told you, this first carbon, fourth carbon and the sixth carbon, now they are in the boat form, and that's why the atoms attached to it, they are going to come closer and they will have this interaction. We call it as transannular interaction. Similar kind of interaction is found with the atoms attached to the fifth carbon, third carbon and the seventh carbon. Now what will happen, we have over here a transannular interaction. In the case of decane also, there are two transannular interaction present here. But now how to avoid the conformational mobility in this case? Conformational mobility can be avoided by reducing this transannular interaction. How to reduce transannular interaction? The two points or the two ways I have discussed in the last lecture. So what is the first way? That is to change the hybridization. So what will happen when I'll change it to the sp2 hybridization, when I'll make it carbonyl group, the carbonyl group will be pointing outside the plane here. It won't come inside, or it will not have any interaction over here. So that's the first case. What is the second case? Adjust or replacement of this CH2 group by the heteroatoms like nitrogen, sulfur, oxygen. We can attach the heteroatoms at this position. So now for example, suppose I have carbonyl group here. So what will happen when I have a carbonyl group here? It will try to go away from the ring and that will become stable in that conformation. It will not change its conformation that from that stable conformation to the other conformation, because now if it will change the other conformation, it may come across or it may come closer to the hydrogen atoms of the or the across the rings, and that's why it may increase the transannular interaction. That's why to avoid the conformational mobility, the first case you can replace the carbon hybridization from sp3 to sp2. Second, you can replace the heteroatoms with like nitrogen, sulfur or oxygen. And now I'm giving you the third way. Third way is to attach the substituents. But where you will attach the substituents? You cannot attach the substituent at the first carbon atom or the fourth carbon atom or the sixth. You cannot attach the substituent at the position where the atoms are involved in transannular interaction. So if you look at this cyclooctane, there are 6 hydrogens, 3 here and 3 here. They are involved in transannular interaction. You cannot replace these hydrogens. Suppose if you replace these hydrogens, so if I have a CH3 group here, that will have a more crowding and that structure will be more disturbing. So you cannot change this. Rather, you try to change the atoms which are peripheral, not the intraannular. Peripheral are these. At the first carbon atom, you can see the axial is intraannular, but the equatorial is peripheral, which is outside the ring, which is not involved in any kind of strain. So what we can do is we can have interaction or we can have a replacement with this group. For example, here what I have shown here, it's in case of cyclodecane ring at the second carbon, both the hydrogens are the peripheral. So I have replaced them with the methyl groups. So now when I'm replacing them with the methyl group, this ring will experience the inhibition for the conformational mobility. Because what will happen if I'll change this? If I'll change this ring, or if this ring will try to rotate, the second carbon atom will be getting involved in this transannular interaction. Because right now we are having this boat where the second is not involved in any kind of interaction. But when I invert the ring, the second may involve in transannular interaction. That's why this ring will be stable or will remain rigid in this form only. Because if it will try to change the structure, the second carbon atom may experience the transannular interaction. So in this case, I have attached the substituent, but which kind of substituents I have attached? Simple small methyl groups. I have not taken any bulkier groups like tertiary butyl group. So with the help of the smaller substituent also, we can change the conformational mobility. Similarly, suppose these two methyl groups, if I'll attach to the cyclohexane ring, you will not experience any kind of inhibition for the conformational mobility. Still, that cyclohexane ring can change to one form to other form very easily. But similar methyl groups, if I'll attach to the medium size ring, they will experience high amount of conformational mobility. So in the case of transannular interaction, the medium size ring, the transannular interaction makes the medium size ring to have an energy barrier for both pseudorotation as well as ring inversion. With the increase of substituents, the conformational mobility can be reduced. This is one of the example I have given you here. The conformational mobility is restricted. How it is calculated? It is calculated using delta G, which is ring inversion energy. That is from changing from one form to other form. How much amount of energy is required? That is being calculated with the help of delta G. So for cyclononane, a simple cyclononane structure, they can change from to one form to another form using energy of 25 kilojoule per mole. But in the cyclononane, at the first position, if I attach two methyl groups, geminal methyl groups, it will have the barrier of 37.5 kilojoule per mole. But right now we can see there are four methyl groups at one position as well as four. This is nonane structure, which is having different structure than this. Huh? So 1, 1, 4, 4. There are four methyl groups here right now, and it is experiencing the highest energy barrier of 88.5, which cannot be overcome. And that's why this particular molecule will remain stable or will remain rigid in the one conformation only. Okay. So that's why as you'll increase the number of substituent, ring flipping can be avoided. In case of medium size ring, you can avoid the flipping even with the small changes. What are the small changes? First is attaching the substituent, even with the smaller substituent like methyl groups. Second, we can change the hybridization of the carbon from sp3 to sp2. For example, changing CH2 group to carbonyl group. Or third one, replacing the CH2 group with the heteroatoms like nitrogen, sulfur, or oxygen.